In today's experiments, we'll be dealing with Newton's second law of motion. So we'll be using terms such as velocity, mass, position, and time to solve these problems. For this experiment, we'll be observing an object's position as a function of time. We'll be doing the experiment twice, one using a real-world model and another way using a computational model. So why do we care about Newton's second law? Uh, Using his second law, we can predict where an object will be over a certain interval of time. So this could be useful if we want to know where like a rocket is going to be, or where a bullet will land. In my case, where an orange is going to be. I don't know why I chose an orange. It was just the closest thing to me. The results I found when experimenting with the real world versus computational model were close, but it wasn't as accurate as I like it to be. As you can see here in the chart, the top line represents the real world model and the bottom line represents the computational model. Yeah, so it's close at the end, I will say, but the middle is not as accurate as I would like it to be. This is Tracker. This is what we use to create our real world model. So in the intro, you saw the orange actually jumping up the counter. This is the actual video. The orange jumping up the counter is just this video in reverse. So the length of this clip is actually only 0.3 seconds long, and because of that, I used a higher frame rate because my theory is the more tracking points you have, the more accurate your predicted position will be. Because if we have more measurements to go by, your final outcome will be just that much more accurate. So yeah, after 0.3 seconds, you can see the slope of the graph is decreasing in the negative y direction because the orange is falling. Yeah, this is our real world model. So this is our computational model in Glowscript. We run it. This is what it looks like. As you can see, the dot goes down the y-axis, and we can see here on the chart, as time passes, the position is moving in the negative y direction. So this is what the code behind the computational model looks like. Ball M is just mass, so this is 0.237. That's the mass of our orange. I googled it because I don't have a scale. Position is calculated from tracker, so this is the position when time is 0, and the velocity formula is change in position over change in time. So we use our tracker data and look at our final position, final time, and beginning time, and we divide those two, and we'll get negative 2.47. So in our loop, we want to set fnet to 0 because the orange velocity is constant, meaning that there's no other forces acting upon it. So this is a huge assumption because in the real world there's like air resistance, gravity, and friction, but for our case, because our velocity is constant, we'll just set that to 0. And this is our velocity update formula and our position update formula. So these constantly update as the loop goes on, and it spits out data that looks like this. So this is actually the Glowscript data. This is the position data as time goes on, and you can see that the Glowscript data is actually a lot more linear because linear than the real world data, because in the real world there's more forces at play, and also there's some human error with the real world model too, because we have to manually place these tracking points, and you're not going to be 100% accurate on the middle of the orange all the time. So there's human factors in that well. So to improve upon the accuracy, we could use a higher frame rate, so more tracking positions. And we could also use like measuring tools such as a scale, so we can note the actual mass of the orange, and we can use a ruler because in tracker, I think right here, yeah, so this is the diameter of the orange. I just googled the average diameter, but if we were to measure the actual diameter of the orange, the graph would probably look a lot more accurate. And this concludes the lab experiment. The final graph is pretty accurate, the end position at least, but I'll definitely be using the methods described to get a more accurate graph in the future. Yeah, thanks for watching.